Just going to wait a minute as I watch the participants, make sure people are getting on here. Good evening, everyone. Thank you for joining us virtually. We're very excited to have you here. This is what we're marking as a keystone event for the Pittsburgh chapter of INFORMS. Many of you are familiar with INFORMS, but we wanted to just give you a quick introduction, and then we'll introduce Professor Hooker and move on to his material because he has a lot of good insight to share with us. Yash, if you could go to the next slide. So our chapter mission, and I just want to emphasize, our purpose is really to connect analytics professionals in the Pittsburgh area and beyond. You'll see in a little bit some of our bios, those of us on the board who will take a minute here and there to introduce ourselves. We come from multiple different backgrounds, and we're just finding the best ways to bring these professionals together in our area. So I'll quickly introduce the board, who you'll see speak throughout the evening. So Yash is our president, Marcus vice president, I'm the treasurer, and Chris is the secretary. And you can briefly see from our bios that we have multiple different backgrounds. And again, I'll emphasize that we may have very strong daily operations in analytics, or some of us might be a step or two removed from those, but we're trying to expand our networks and make sure that we're interlocking and getting to know each other and finding ways to be helpful to each other. So I'll pass the mic on to, I believe, Marcus.
All right, thank you, Annie. So as Annie just mentioned, we're a relatively new chapter, so we thought it makes sense to say a few words about our goals. So really what we're trying to do is to bring together people who are, broadly speaking, interested in analytics, whether it's OR or data science or stats or math or computer science. This is really meant to be a platform, a forum for everyone that's interested in that space. So we want to line up top speakers as we are doing today to share with you, interesting topics and insights, and just, again, be a forum to enable networking to get us to talk about best practices and really all things that are happening in this space. If you go to the next slide, please, Yash, some of the activities that we've got lined up. So again, presentations just like today. We're also facilitating panel discussions to talk about, again, topics of interest. Go through software tutorials, give graduate students a chance to talk about and showcase the work that they're doing, help students and young professionals review resumes and with interviews, and hopefully host in-person happy hours soon too. If we go to the next slide, I'll just again emphasize that if you're interested in becoming a member, that would be great. This is really meant to help with networking, give you a forum to talk about best practices, lessons learned. We're looking to interface closely with the student chapters and really just be a great community across the board. So with that, I'll pass it along.
With that, it's my great pleasure to introduce Professor Hooker today. I think a lot of us have CMU connections. A lot of us know him very well already. His research interests span optimization, constraint programming, ethics of business, even music theory. I was surprised to find out recently. So Professor Hooker does a lot of very interesting work in a lot of different domains. He's a recipient of the INFORMS Computing Society Award, as well as the Khachiyan Award, amongst many others. I think on a personal note, I took Professor Hooker's class 11 years ago, and I still use his notes sometimes. And what really struck me during the class was how elegantly he explained complex mathematical ideas and concepts. And I'm looking forward to him touching upon a very interesting topic with the same elegance that he taught us linear programming. So that I will stop sharing my screen. Professor Hooker will, I think, briefly talk for maybe about 50 minutes. That's the goal. If there are any questions that any of you have, please feel free to keep posting them with the Q&A button of this webinar. And I'll keep bringing them up to Professor Hooker as and when I see them. So the floor is all yours, Professor Hooker.
Okay, let me share my slides. All right, so thank you very much. It's great to join the Pittsburgh chapter of INFORMS. And it's also great that we have a Pittsburgh chapter, since after all, Pittsburgh is one of the birthplaces of operations research. Did you know that the first OR model to be solved by computer was solved in Pittsburgh? This is back in the 1950s by Bill Cooper. It was an oil refinery model. And of course, we've had many advances in OR in this city since then. All right, so the topic today is how to model equity and fairness in optimization models and AI applications. So why talk about this? So actually, we're seeing quite a bit of interest lately in going beyond the usual objective functions. The usual objective functions are minimizing cost, maximizing profit, maximizing benefits of some kind. But there's growing interest in finding fair and equitable solutions as well as efficient solutions. An example would be healthcare, the obvious application where fairness is important. Facility location. In fact, I worked on this problem many years ago. That was my PhD thesis in OR. If we have, say, ambulance stations, how do you locate them? You could locate them to minimize expected or average response time, or you could locate them to minimize the worst case response time, so no one is left out. Two extreme solutions to that problem. One of them focuses on fairness and the other on efficiency. Okay. Telecom has for many years been a major consumer of equity models. So there's something called Jain's Index, J-A-I-N, which is widely used in telecom. Also, the Nash bargaining solution, which engineers know as proportional fairness, has been used in telecom for a long time. So here, the idea is that you want to have maximum throughput through your telecom system, but at the same time, without penalizing any particular source of signals disproportionately. Traffic signal timing. Now, I live part of the year in Los Angeles, and I'm pretty sure that the intersections around where I live use proportional fairness to regulate traffic signals. So if you think about it, suppose you have an intersection of a major street and a side street, okay? What's the most efficient way to time the green light? Well, you should give the green light to the major street all the time. That will maximize throughput of traffic. Not very fair because it keeps the people on the side street waiting forever. So what engineers do is to compromise between fairness and efficiency. And one way to do that is the Nash bargaining solution or proportional fairness. Another major application recently is disaster recovery, of which we've had all too many in recent years. One example might be Hurricane Maria, which hit Puerto Rico a few years ago. It was the worst storm ever to hit that island. And well, there are two ways to restore power after the hurricane. One is to focus on efficiency by restoring power to urban areas first. And that's the way it was done. Okay? Because this is where the population is concentrated, so you benefit the greatest number quickly. On the other hand, that left people in the rural areas without power for a very long time, sometimes even several months before the crews got out there to take care of them. On the other hand, if you have a purely equitable solution and try to equalize everyone's benefit, then you're going to have your crews cruising around the countryside for weeks while many more people in the cities are doing without power. And that doesn't seem reasonable either. So we need somehow to balance the equity and efficiency in a case like this. Now, how do you formulate equity along with efficiency in an optimization model? It's not obvious, okay? So it's fairly straightforward to write down a formula to minimize cost. Right? You just add up the costs or maximize benefit or maximize health outcomes, whatever. But when you have equity or fairness, there's no consensus on how to do that. And it's not obvious at all. So we're going to look at that issue. And that's because there's no one concept of fairness out there. There are several concepts, and different concepts may be appropriate for different applications. So what I'd like to do is to take you through a quick survey of some of the concepts that people are using nowadays and have discussed. Look very briefly at their mathematical properties, the pluses and minuses, and very briefly how to model them. How do you write an optimization formulation of these formulations of equity? And as we go along, I'll take just a brief excursion into social choice theory, which provides some kind of theoretical background for a few of these solutions. Okay, so that's the agenda. If you'd like to pursue this in greater depth, I do have a much longer tutorial, which you can find online, which I presented at the Constraint Programming meeting recently. I also wrote a survey paper with my student, Violet Chen, which you can click. It's online as well. And all the references I'm going to show you are in that paper. Okay, so as I say, I'm going to take you through some possible ways to formulate fairness and equity. One of them is inequality, how to measure inequality, if that's your concern. Fairness for the disadvantaged, for example. And you'll notice I'm classifying these in a couple of ways. There are a couple of properties I'll mention in a moment that you can use to characterize them. The Pigou-Dalton condition and the Chateauneuf-Moyse condition, I'll mention those. Also, we're going to characterize these models by whether they add nonlinearities to the problem. Maybe you don't want that. Most of them end up being linear, but a few are not, okay? And also, do they add discrete variables to the problem? Most of these that you see do not add discrete variables, but one of them does. And of course, discrete variables can make the problem harder to solve. So I'll characterize them that way as well. So in addition to these two classes, I'm going to look at combinations of efficiency and fairness, convex combinations, some classical approaches, particularly alpha fairness. And I mentioned the proportional fairness or Nash bargaining solution, which is a special case of alpha fairness. And an alternative to that, known as the Kalai-Smorodinsky bargaining solution. Some more recent work, including some of my work, deals with threshold approaches, threshold functions to combine utility and efficiency. And then I'll wrap up with what people are doing in the machine learning world, which is to use statistical fairness metrics, along with something called counterfactual fairness. Okay. So that's the agenda. So if you have questions or issues, I hope you will post those in the question window, and we can deal with those as we go along, or afterwards if you prefer. So what I'm going to do is formulate equity using a social welfare function. This is a concept from economics, been out there a long time. So a social welfare function is a function that quantifies how good things are in our distribution. And what are we going to distribute? We're going to distribute something called utility. This is a concept that goes back to Jeremy Bentham, 200-300 years ago. And what is utility? It's whatever you want it to be. Usually it's something like profit, negative cost, health outcomes, benefits of some kind. It's what you're concerned about. Now, these U's here represent how we're going to distribute utility across individuals or across groups or institutions. So we're concerned partly with the magnitude of the utility. We want things to be better, okay? And also we're concerned about how the utility is distributed. Is it a fair distribution? And the social welfare function, the W, measures how good that distribution is with respect both to the magnitude and the spread of the utilities. It's a way of measuring social welfare. Okay. We're going to use this as the objective function in an optimization model. So the idea is you have a model that you've built. And rather than put the usual sort of objective function, minimize cost, maximize profit, we're going to use a social welfare function as the objective function so that we take into account equity and fairness as well as total benefit or minimum cost. Okay, that's the idea. So we want to incorporate somehow both the total benefit and the fairness in this social welfare function. So the task before us is to decide how to write that social welfare function and which one we should select. So I'm going to formulate the problem like this in general. So we're maximizing social welfare, okay, as a function of this distribution of utilities or benefits. And the utilities are themselves a function of the distribution of resources. So usually in a model, we have resources we're distributing, okay? It could be equipment, manufacturing or labor, whatever it may be. And the utility that each individual get is a function of the resources allocated to those individuals. So that's going to be expressed by this utility function. And then the resources themselves, of course, are subject to constraints on the resources and how they interrelate. So this is incorporated in the optimization model you begin with. I'll give you a simple example. In fact, I'm going to show you this example in some detail later on. So example runs like this. Let's suppose we have a medical triage problem. That is, we have some patients need to be treated, but we have limited resources. A problem that's all too common nowadays, isn't it? In our crowded hospitals. We have limited resources. Okay. So the utility we're going to measure, the utility of a patient, U, is measured in terms of quality adjusted life years, which is standard in this field. This is the number of years this person can be expected to live, factored into the quality of life as well, of those years. And the resources are going to be the medical treatments that are available, all right? So we're writing here the utility to be a linear function of resources in this particular case. Okay? And we're taking the resources to be a 0-1 decision. That is to say, we're going to provide the treatment to this person or not. So 1 means the person gets the treatment. Then we have a budget constraint because each treatment costs money or requires certain resources, and we have a total limit on the resources available, a budget constraint, okay? And then we maximize social welfare measured somehow with respect to these constraints. That would be an example of what I'm talking about. All right, now to simplify matters a little bit, I'm going to get rid of that utility function, this U, and just factor that into the constraint set. So the relationship between the utility distribution and the resource distribution is going to be encoded in the constraint set. So I don't have to worry about writing utility functions separately. Okay. Now, I mentioned these two conditions. The Pigou-Dalton condition is often used to assess whether an equity criterion is appropriate. And it says, if you make people more equal, then things get better. Equality is good. So in particular, if you take any two individuals and move them closer together, this should increase social welfare, or at least not decrease it. And if so, you satisfy Pigou-Dalton condition. Okay. Now there's a problem with this condition. And that is when you decrease the inequality between these two individuals, which is good, you may also increase the inequality between the top individual and anyone above that person. And of course, similarly for the person on the bottom. So whenever you decrease inequality this way, you're also probably increasing inequality, which is not what you want to do when you measure this criterion. So that's a problem. One way to address this problem was proposed by Chateauneuf and Moyes, and they suggested we should check what happens when you take a group at the top and reduce their utility by transferring it to a group on the bottom so that you squeeze the spread or the range of utilities. This way you avoid that problem I described because there's nobody above the top group and there's no one below the bottom group. And then when this happens, you want to make sure that we increase social welfare or at least don't decrease it. This is a weaker condition than Pigou-Dalton. So I'm going to be looking at both of these when we classify these social welfare functions. So these are the inequality measures that I mentioned. As you can see, they all satisfy both of these conditions. Okay, so that's good. In fact, equality measures are the ones that really should satisfy them. And none of them have discrete variables in the model, and only one is nonlinear. Okay, now, is equality really what we want to measure in applications? Is this really what matters? How important is pure equality? Well, actually, I have a background in philosophy as well as OR. So I've done a lot of reading in this area. And I have to tell you that philosophers have absolutely no consensus on this issue. So they're not much help to us. So basically, there are two views. One view is that equality is bad, inequality is bad only to the extent that it actually reduces total utility. Okay? Because when people are unequal, well, that creates problems. It creates people who are dissatisfied. It incites instability. And of course, the people on the bottom are proportionately worse off than the people on the top benefit as you have inequality due to the concave nature of utility curves. Okay. So there are certainly utilitarian consequences of inequality. And this school of thought says this is the only problem with inequality. There's another school of thought that says that inequality is irreducibly bad, even if it doesn't have any effect on total utility. It's just something we don't want to have. It's irrational. Okay, so there's those two. And then even if we can get around that issue, there are some other problems with inequality measures, with using these. And one is they don't care how well off we are. So if you take a population and improve everyone's welfare, but retain the same distribution, the same relative welfare, then that's not recognized. It's no better by an equality measure. Another problem is that inequality measures don't care about the top versus the bottom. So reducing inequality among billionaires is just as good as reducing inequality at the very bottom, where you move some people up from dire poverty. Okay, so it's just as no better to move people out of dire poverty as it is to move some super billionaires down to not quite so super. They're both the same because they reduce inequality the same amount. So these are two reasons that one may not want to use a pure equality measure. So you can decide if it's appropriate. So equality, at least we have a consensus that it's not the same as fairness, although it's related. Okay, so you can decide whether your application requires pure inequality. Now, how do we measure it? I'll show you 3 or 4. The simplest is just the range from top to bottom. How spread are people from top to bottom, normalized by the mean? Okay, very simple. Now, I wanted to show you this because this illustrates how we can linearize this measure. See, it's not linear, obviously. It's a ratio of fractions. There's a number of these measures we can linearize by using linear fractional programming. We just use a change of variable that allows us to set the denominator, which is the mean, equal to 1. Okay. So this was introduced in Pittsburgh. Okay, since Pittsburgh, after all, is one of the origins of OR by Charles and Cooper way back in the 60s, and still used today, and it's very useful in inequality measurement. So this linearizes the problem and makes it a linear programming problem if the original constraints are linear. All right. Now, suppose the original constraints are not linear. Well, they may be homogeneous, in which case we get another homogeneous set of constraints. And if they're linear, we just get another linear set of constraints with different variables. Okay. Now, from here out, I'm going to assume, just for convenience, that the original constraints are linear. Actually, this is not much of a restriction because you can use piecewise linear approximations of almost anything. If you have a convex feasible set, for example, you can use a piecewise linear approximation. But so it's not a strong assumption, but I will make this assumption so I can refer to whether the resulting model is linear or not without worrying about the linearity of the original constraints. Okay. Another measure is relative mean deviation, okay, which can be linearized. Okay. It's normalized by the mean utility. Another one is basically the normalized standard deviation, called the coefficient of variation. It's very familiar. It has that advantage. People are familiar with it. Okay. Now this one is nonlinear. Okay? But at least you can get rid of the square root and make it a convex problem. You're minimizing a convex function. Okay? And perhaps the best known, I'm sure you've heard of it, is the Gini coefficient. Okay? Gini coefficient is based on the Lorentz curve, which is the cumulative utility distribution curve. And it's defined to be the area, of this blue section, divided by the area of this entire triangle. All right. And a nice thing about Gini, you can linearize it using the same change of variable I mentioned before. So you get a linear programming problem. All right. Now there's also something called the Hoover Index. Okay. Hoover Index is actually basically the same as relative mean deviation I showed you a moment ago. It has an interesting geometrical interpretation. Rather than being a ratio of areas above the Lorentz curve to the triangle, it's proportional to the maximum vertical distance between this diagonal and the Lorentz curve. Okay, so the longer the distance, the more inequality we have. And in fact, you can interpret it as the fraction of total utility that has to be redistributed to achieve perfect equality. So it's a very natural measure of inequality. And it has this same linear model as relative mean deviation. Okay, all right, so that's inequality measures. So why don't we move on to fairness for the disadvantaged? All right, so the most famous of these, so here we're taking into account the welfare of the worst off in our fairness measure. The most famous is the one proposed by John Rawls, probably the most famous philosopher of the 20th century. He called it the difference principle. And he suggested that inequality is justified only to the extent that it increases the utility of the worst off. And as a result, we should maximize the welfare of the worst off. That should be our criterion. Take care of the people on the bottom and maximize their welfare. All right. So let's see why he thought that. I can give you a very quick summary of the argument. It's a social contract argument. He says, suppose we get together into a constitutional convention to design our society. Now, how are we going to design it? How are we going to design the institutions and the economy? Well, some people are going to end up on the bottom in any economy, and some people are going to be well off, okay? So he argued that we want to have consensus on this society. And if we're going to have consensus, everyone's going to have to be satisfied with the possibility that they're on the bottom. And the catch is, you don't know if you're going to be on the bottom until we've already decided on the structure of society. You have to make this decision behind what he calls a veil of ignorance as to who you are in the world. Then later you find out who you are. Now, you may end up on the bottom, and you have to be prepared to accept being on the bottom if that happens to you. And the only way that we can be all prepared to accept being on the bottom is if no other social solution would have made us better off if we were on the bottom. In fact, any other solution would make us worse off being on the bottom. In other words, we should maximize the minimum. Okay, that's his argument in a nutshell. All right. Of course, the model for this is very simple. You just maximize the minimum, which is easily linearized. Okay. Now, this seemingly reasonable criterion has some strange implications. Suppose, for example, you have a couple of patients who need treatment, and your utility function is linear, and you have a budget constraint on the resources available. That means the feasible set for your utilities of the two patients, that feasible set is a triangle. It's a linear constraint, okay? But this is patient two. Patient two is harder to treat because if you devote all resources to that person is going to have less utility than patient one if that patient gets all the resources over here. All right. Now, the maximum solution is to equalize the two. And this is that solution. But look what happens. The patient who is healthier is asked to sacrifice a great deal to bring the solution to equality. Okay. In other words, we're bringing this relatively healthy person down to the level of suffering that must be endured by the more seriously ill person. who's harder to treat, which seems pretty extreme. Okay. And there's another strange consequence. Let's suppose we simply have upper bounds on how much utility we can achieve for these two individuals. Then a solution that equalizes utilities has the same social welfare as a solution that gives the excess utility to patient one. So these two solutions are equal from a point of view of the social welfare function, but one patient, one solution uses all the utility and the other solution wastes most of the utility. It just throws it away. It seems odd as well. All right. One way to get around this partially is to use a Lexamax. Okay, that is, you maximize the worst off, then you hold that fixed and maximize the second worst off, and so forth. So you can do that. That requires solving a sequence of optimization problems. But I have to tell you, to get a true Lexamax, you have to enumerate all the ties, if there are ties in the solution, and that can grow exponentially. Okay, so it's in practice, it could be rather tricky to solve the problem. There's also something called Maclune Index, which is rather widely used in public policy, particularly education. And this is an index that only cares about people in the bottom half. So basically it's saying it's all right to have people who go to elite academies. We'll tolerate that. But we don't want anyone that's below the median going to inferior schools. We want to bring everyone up to the median. And if you do that, if everyone's brought up to the median who's below it, then this is the maximum score on the Maclune Index. Okay, so that's the rationale for it. Unfortunately, the model for it is a MIP, a mixed integer programming. You got integer variables, you can't avoid it. Okay, so it's a rather complicated model. You also have to linearize as well by changing variables, so you get this model. Okay. Okay, so that's some of the criteria that take care of the worst off. Now, these criteria can be derived in the traditional social choice theory. This goes back to the 1950s, Kenneth Arrow. And what they do is to adopt some axioms from which you can derive certain social welfare functions. All right, so these are typical axioms. Anonymity, everyone basically counts the same. Strict Pareto, if you improve everyone, then it's better, then we have a better society. Independence and separability. So you can look at these later if you're curious. So we have fairly reasonable axioms here, but there's another axiom that's often forgotten, and that's a degree of interpersonal comparability. So this tells us to what degree you can compare the utility level between two persons. Does it make sense to say that my utility is twice as much as yours? Can you measure that? Or does it make sense to say that my utility is 15 units more than yours? Okay, to what degree can you compare? Well, this comparison is assessed by these transformations, invariance transformations. Invariance transformation is one such that if you apply it to two distributions of utility, it doesn't change the ranking, the relative ranking of those two distributions. Okay. So there's two big theorems in this area. One begins with something called unit comparability, which means that you can compare utility differences. So this means that if you have two distributions, U and U prime, and if you start out with one guy who has more utility than another guy, when you compare the two distributions, that's to say this distribution benefits one guy, person I, more than it benefits person J, then that comparison remains after you apply the invariance transformation. All right. There's a certain degree of comparability, not a great deal. And given this, you can prove that the utility function, the social welfare function, must be the sum of the utilities, what we call a utilitarian function. You know, it seems like a very strong result, but I'll come back to that in a moment. Another one is called, another criterion is based on level comparability, which means that the ranking of two individuals in a utility distribution is invariant under a transformation. Okay, you can compare it so-called level comparability. And here, if you assume these axioms, then you derive that Rawlsian maxim-in criterion. It's the only solution. Again, seems like a very strong result. Okay. The problems with this is that the assumption of a certain degree of interpersonal comparability means that you have no more than that degree of interpersonal comparability. So with unit comparability, you're assuming you have no more. And this allows you to derive a utilitarian criterion. The proof is quite interesting. It's a clever proof, but it's a very strong assumption. And then if you assume that there's no more than level comparability, you can derive the Rawlsian criterion. But again, that's a very strong assumption. In fact, it's so strong that it rules out every other criterion of social welfare I'm going to show you today. Okay, it's that strong. So yeah. Okay. So at this point, I'm going to go a little bit faster so we can cover it. I think I've covered the main concepts here. Then I'm going to show you some more of the different criteria people use. One set of criteria is to take convex combinations of utility and equity. Okay. Here's an example. The problem with these criteria is you have to use some kind of multiplier when you make a convex combination, and you don't know how to choose that multiplier. You don't know how much weight to put on the two criteria. Okay, so it's like multi-objective optimization, but you don't know how much to weight them. And there's no way in principle to know. In fact, in this case, you're comparing quantities with two different units. You know, one is dimensionless and the other is not. Yeah. And you get the same sort of result with the other possibilities. So it's not a very promising way to go, frankly, to try to take a convex combination of the two criteria because you don't know how to combine them. Okay, so let's move ahead to some of these classical, very interesting classical methods for combining equity and efficiency. One is alpha fairness. Okay, it's widely used in engineering. So basically the formula for alpha fairness, the social welfare function is this. It's really nothing more than the integral of a power law. Okay, very simple. You can derive this axiomatically. It has been done. Okay, just in a very recent paper, this has been done. Okay, so at one extreme, when alpha is 0, you have a utilitarian criterion, and when alpha goes to infinity, you have a maximum. And everything in between balances the two in some way. So it has that nice property. You have a continuous adjustment of the importance of equity, and it satisfies Pigou-Dalton. All right. This is why it's widely used. It's very nice properties. It is nonlinear, okay, but at least you're maximizing concave function, which is not too hard. All right. Now, problems. This alpha does have an interpretation mathematically, but in practice, you don't know what value of alpha to use. Okay, you just sort of have to pick one that sort of gives reasonable results, maybe, but otherwise, it really has no connection with application. Nonetheless, it is widely used because you just pick an alpha that seems to give reasonable results and everyone's satisfied with. Another consequence is that you can show that a solution in which everyone is equal can actually have the same alpha function value as another solution in which you have infinite inequality. That's a bit surprising. Okay. Special case is when alpha equals 1. And that's when you get proportional fairness. Okay, this is the one that John Nash derived. By the way, John Nash also studied in Pittsburgh, right? In fact, he was a student of my former colleague, Jerry Thompson, who got him into the Princeton PhD program in OR by writing a one-sentence recommendation letter. He said, John Nash is a mathematical genius, as he was. And this is actually his first paper. This came before his paper on game theory. All right, this paper on the Nash bargaining solution. Brilliant paper, absolutely brilliant. And he derived this criterion axiomatically in a very nice proof, beautiful proof. All right, even though the assumptions are quite strong. And it's got a great geometric interpretation. So for example, I thought I had a picture here. Oh, that's my picture. Anyway, it has a very nice interpretation, and that is that this is actually just the product of utilities. And in other words, you're taking maximum value, a maximum volume of the hyperrectangle that's described by these utilities. You maximize that volume. So it's a nice interpretation. It can also be derived from a bargaining argument. If people bargain in some rational way, they will arrive at the Nash bargaining solution. Okay. Problem with this is that there's a whole school of thought that questions whether a fair bargaining process leads to a fair outcome. So, for example, you may argue, well, suppose we have a free market and everyone's allowed to bid for goods, okay? And everyone's allowed to go into a store and buy at the price. Does this result in a fair distribution of wealth? Well, maybe not, okay? This is, a deep issue in political philosophy. So the bargaining solution is sort of take one side of that philosophical issue and say, yes, procedural justice is enough. But there are others who say it's not enough. So you can make up your mind on that before you choose one of these. Now, there's a problem with the Nash bargaining solution that was addressed by Kelly and Smordinsky. It's an interesting problem. So their solution goes like this. Okay, you have two players here, okay? You look at the maximum utility you could devote to either player if you gave them all the resources, the two ideal solutions for the two players. Then you plot those two coordinates, okay? Then you draw a line from the origin to that point, okay? And then the distribution of utility is the intersection of that line with the feasible set, which is this black line here, what's below the back line, okay? So that's the Kelly-Smordinsky solution. Now, the problem that I mentioned is that suppose you enlarge the feasible set like this, okay, to form the green region. Now, if you enlarge the feasible set, it turns out that one of the parties in the Nash solution, which is up here, actually ends up with less utility after you enlarge the feasible set. Okay, and this problem is solved by the Kelly-Smordinsky solution. So that was the motivation for it. Okay, this is how it looks mathematically. This solution, by the way, Kelly-Smordinsky, basically says that you maximize the fraction of each player's maximum utility on the condition that that fraction be the same for all players. Okay, so it's sort of like a Rawlsian criterion, except you're talking about proportional shares as opposed to absolute shares. And this is actually consonant with a philosophy that was developed in Pittsburgh by David Gauthier, who's at the University of Pittsburgh. It's called contractarianism. And one of the conclusions of contractarianism essentially is that we should use the Kelly-Smordinsky solution for distributing utility. Interesting, huh? Okay. This criterion actually turns out doesn't satisfy either of those conditions I mentioned. Okay. Yeah. And, in some applications like medicine, you have a problem because, it says that a person who's seriously ill should be allocated the same fraction of his or her maximum utility as a person who's only has the flu. Okay. And that may seem, rather unfair to the guy who's seriously ill should perhaps get some kind of priority here. On the other hand, it does seem reasonable for wage negotiation, price negotiation, and business applications like that. Okay. Now, there are these threshold methods, which I'll mention briefly. They were originally proposed by Williams and Cookson. There are two of them, utility threshold and equity threshold. They're interesting. So this is the utility threshold. What it basically says is, here we have two players, okay, and the feasible set is under this curve. Okay. Now, you might regard this as two patients, again, who need treatment, and we have limited resources, but patient one is much harder to treat, so you can't provide much utility to this patient, okay? Now, the maximum end solution is here, okay? But this, again, requires patient two to sacrifice a great deal, and any improvement in patient one at this point incurs an enormous sacrifice from patient two. Okay, and this may seem extreme. Well, an alternative is past a certain point, you switch to a utilitarian criterion, and that's shown by these contours. And if you do that for this particular breakpoint, then the optimal solution turns out to be up here, which is more of a compromise. between maxim-in and utility. Okay. So this is parameterized by this delta. Okay. Now, this can be generalized to N persons, which I worked on with Paul Williams at London School of Economics. The generalization is not obvious, but it comes out to be this formula. And here the delta has a practical application. You choose this parameter delta, which is something like the alpha before, but only now you choose the delta so that everyone who's within delta of the lowest is everyone who's close to the lowest guy is going to get priority. And people who are better off above the delta don't get special priority. Okay, so in other words, you interpret the delta as how badly off you have to be to get priority. Okay, so maybe you get make some degree of sense in an application. And it goes from utilitarian to maxim-in. So it's a combination of utilitarian and maxim-in in a particular way. Okay, and the model looks like this. It's a MIT model, but it turns out it has a very tight model. It's a convex hull relaxation, so it's very tight. Okay. The other is an equity threshold. Okay, so this one is the opposite. So here you begin with a utilitarian, but if you go, if things become too unequal, you switch to a maxim-in. Okay, so this seems to be more appropriate for disaster relief type of problem as opposed to a medical problem. So disaster relief, you want to give, benefit the most people as possible quickly, but not to the point where you overly deprive people who are out in rural areas. So once you begin to create too much unfairness, then you switch to maxim-in. Of course, it's more complicated when you have many players, but that's the basic idea. And this again can be generalized to N persons. It looks like this. And the delta, again, has a sort of a real-life interpretation. It says basically that if your utility is more than delta above the worst off, then we're not going to be concerned about giving you more, even more utility, unless the guy on the bottom also gets more. Okay, so you read it like that. Okay, so we have a question. As an engineering student, I wasn't exposed to the concept of fairness. What can be done in education to prepare engineers? Where should this be? Okay, I think it should be in their engineering class. Okay, because it's an optimization problem. It's a problem of modeling. To the extent that we teach modeling in engineering, and we often do, okay, we should teach how to model equity just as much as we teach how to model cost minimization. Okay, it's part of the modeling task. Okay, another question, how can we handle utilities that are random? As decision maker, we may not know what individuals care or prioritize. All right, well, those are sort of two different questions, right? So the utilitarian outcome maybe have a random element, okay? Well, after we make our decision, how to do that. That turns out to be a very interesting question that I've worked on with a couple of my colleagues, okay? Because it turns out, it's a long story, but it turns out that, these random problems basically boil down to two-stage optimization. It's optimization with recourse. And the recourse, takes into account the random element. So at what point do you integrate the fairness element? You can do it in two different ways. And it's a sort of a fundamental decision how you do that. So it's a very interesting question, how to resolve that. And that's on the research frontier. And we are working on that right now. Yeah, interesting question. Okay. All right. So I was mentioning this alternative threshold method, and it has a nice linear programming model. Okay, so it has that advantage. Okay. So I'm going to move on to another alternative, because it turns out that these threshold models have a weakness because they combine utilitarian with maxim-in. And I showed you some of the problems with maxim-in. It only cares about the very worst off. It doesn't care about the utility position, the equity position of people who are better than the very worst off. So as a result, this is sort of a limited way of accounting for equity. And one way to do that is to use a similar threshold approach to combining utilitarian with a Lexamax. Again, this is much harder to do theoretically because you have to solve a sequence of optimization problems, and the model is more complicated. But it turns out in practice, this model is relatively easy to solve. So I'm going to show you an example of that in a moment. So that is one approach you can use. Also, you can develop valid inequalities for this MIP model, and that helps make it easy to solve. Okay. So let me just push ahead to an example. Yeah, this is the model for the threshold, the utility in Lexamax. It looks like that. So as you see, the integer programming problem is a bit involved, but who cares as long as it solves, right? Okay. So let me show you a couple of examples. Okay, and these examples will compare two of the threshold methods, one combining utilitarian with maxim-in, and the other combining utilitarian with Lexamax. And we're using the utility threshold. That is, we're focusing on equity until utility is sacrificed to a great degree, at which point we switch some of the individuals to a utilitarian measure. So that's the first one I showed you. So I'm going to, this problem was inspired by the National Health Service in the UK, because my co-author was at London School of Economics, and we had some contacts in the National Health Service. So we have a limited budget to provide treatments to the general population. In particular, we have a number of disease categories that require different types of treatments that have different costs. And we want to allocate limited funds to these treatments where they're most needed in some sense, but do it in an equitable way. Okay, so this is a public decision, right? So this is transparent. The public scrutinizes it. It's much like Medicare in the US, which makes similar decisions of this kind. What kind of treatment to fund and when. Okay. So as I mentioned, I'm going to compare these two types of social welfare functions. So these are some of the data. We have various types of conditions that require treatments. So we have people who need pacemakers, hip replacements, aortic valve replacements. This is heart bypass surgery for different types of heart conditions. And in each of these groups, we have subgroups that are divided up by the severity of their condition and their prognosis. Okay, and we have various data, cost data, qualities with and without the treatment, and so forth, and the relative number of people in each of these categories. We have these data. Here's some more. We have heart transplant, kidney transplant, kidney dialysis, okay, and we have which is grouped by the expected survival, okay, and then within those groups, we have subgroups by the severity of the disease. All right, so we have, say, those groups of treatment categories. The model looks very similar to the one I showed you before. It's basically the same. I won't go through the details, but you have a linear utility function based on, that computes the number of quality adjusted life years, based on a discrete decision as to whether to issue the treatment to that particular subgroup. All right. The idea being that you want to be consistent, right? If you decide to treat a certain type of condition, you want to do that consistently so you don't exercise favoritism for a certain part of the country or whatever. And that gives rise to this optimization problem. So it's a MIP model, a mixed integer programming model. So first I'm going to show you the solution in which we combine utilitarian and maxim-in based on this parameter delta I mentioned. So when delta is 0, you have a purely utilitarian. We just maximize bang for the buck, get the most medical benefit for the investment. At the other extreme, as the delta goes to infinity, we get a maxim-in. So we're maximizing the welfare of the worst off patient, taking care of the worst off patient first. Okay. Now, what do these colors mean? Well, for each of these treatment categories, the color means that we're funding treatment in that category. And whether we fund depends on the delta parameter. All right. And at the bottom here, we have the average number of qualities per patient. This is the average utility. Okay. Now, you can see the basic pattern here is that when the delta reaches about 4 or 5 quality adjusted life years, we start switching our resources away from bypass surgery to kidney dialysis. So why? Well, the reasons are a bit complicated, but the basic reason is that kidney dialysis is very expensive, okay, because it's an ongoing treatment, whereas heart surgery is a one-time treatment in most cases. You get it over with, and that's the end of it. So as a result, you get fewer benefits for investment. On the other hand, the kidney dialysis patients are worse off, particularly the worst of them are worse off, because it turns out that patients who get bypass surgery actually do fairly well without the surgery. Okay, surgery is beneficial on the average, but they're not that badly off without it. They often do quite well without the surgery. That's not true of dialysis. You have to have it. So they're worse off. So this is why we switch to them for most of these categories, as the delta increases, as we emphasize equity and fairness more strongly. Now, some of the other variations here are quite subtle. We can talk about those maybe later, but yeah, it's nuanced. Okay. Now, what happens if we combine utilitarian with a Lex-Max? You see how different it is. The shift from bypass surgery to dialysis occurs much sooner, in only about 1 year as the value of delta. This means that if you're 1 year worse off than someone else, then we start worrying about equity. Whereas before, you had to be like 4 or 5 years worse off than someone else before we worry about equity, roughly speaking. Okay. And also, the details are much more nuanced and complicated because it takes into account all of these factors. And the basic reason is, in the equity side, as we become more equitable, we're not just worried about the worst off, we're worried about everyone who's not too well off, okay? In fact, the closer you are to being the worse off, the more priority we give you, but you still get some priority on this criterion. So you get a sort of more reasonable and more nuanced result. So this is worth, mulling over quite some time. Think about what's going on here, I think. Now,
Professor Hooker,
yeah,
sorry to interrupt
yes.
you. There's a question for you in the Q&A tab, which I think you kind of touched upon, but I think it would still be curious. The question is, how can one account for the case when among the set of individuals for whom we aim for equality, there's a subset of them that have been treated unfairly in the past? And
yes. So
yeah.
That comes up in the AI example I'm going to give you next. I'm going to address that very question. Okay, it's a fundamental question, absolutely. So that's coming up in about 1 minute.
Sounds good, thanks.
Yeah. Okay, so let me just show you one more example, and that's disaster preparedness. This is based on a problem in Istanbul, and the problem is, how do we locate shelters to which people can go after an earthquake to find food and water and so forth, okay? And here we have the delta on the bottom, and the utility is negative utility because we're measuring the distance to the shelter to which you're assigned, all right? So we want to get close as possible, but not everyone can be close, okay? So as we become more equitable, then more and more people are within delta of the lowest. So this is what the green region means. Now, the problem here is that there are some people who are just far from all the possible shelter locations. So we take care of those guys first. And once we take care of them, they're still the worst off. So the equity part of this only cares about these people on the very bottom. So as a result, you don't see much of a shift in allocation as equity increases. There are some minor variations, but you don't see what we're really looking for. Whereas if you combine utility with Lex-Max, you see what you're looking for. If we emphasize equity more and more, true, we take care of the worst off first, but then we start taking care of others that are near the bottom, and they get a better and better lot as we increase the emphasis on equity, okay? And some of the people who are well off, pay a price, suffer a little because they're sharing their good fortune with other people as equity becomes more important. So again, you have a lot of nuance here, but this seems to capture in a very interesting way what you want to happen in a situation like this. Okay, So now we're going to wrap up with statistical fairness methods, and I'll address that question. So this is comes out of machine learning. It's a very much discussed idea. And here what we do is to compare two groups, usually a disadvantaged subgroup like a minority group versus the majority. And we want to make sure that we treat these two groups the same in some sense. We want to be fair in that sense. Okay. All right. Now, how do we do that? Well, we have to start by measuring what it means to treat two groups the same. What does that mean exactly? Well, that's measured in many different ways. Actually, it's been measured in 70-something different ways. But I'm going to show you some of the basic ways it's measured, some of the basic metrics. Now, why is this a problem? Because we have discrimination based on ethnic group or race or whatever. And it goes like this. Even if you don't treat the machine learning mechanism in such a way that you tell it a person's ethnic background, still there's implicit bias. For example, suppose you have a low-income neighborhood. Some people in this neighborhood live there because they've been financially irresponsible in the past, so they can't afford to live anywhere else. Other people may live in the same neighborhood because of historical discrimination against their ethnic group. All right? They can be there for two reasons, two causes. Now, if we want to award a mortgage loan to someone in this neighborhood, what do? How do we decide? Who is going to repay the loan? Well, the machine learning device looks at the history. It looks at a training set. And it says that, well, people from these low-income neighborhoods have defaulted more often than people from other neighborhoods. And when you use that correlation that's been observed, you end up discriminating against people who are in the low-income neighborhood for reasons that have nothing to do with their financial responsibility. It has to do with their ethnic background. Okay, so there's hidden bias in these decisions, even though we don't explicitly take into account a person's race or gender or whatever when training the machine. Okay, so we want to root out this problem somehow. And this is the problem that's basically an obsession with this community. How do we get rid of this? So we use the statistical fairness measures to measure the degree of inequality in various senses. And one of them is, simplest one is demographic parity. This basically says that you award mortgage loans, for example, to the same fraction of people in the minority group as in the majority group. It's the simplest. It's not satisfactory because it may turn out that the minority group is actually more qualified for a loan than the majority, and you're forcing them to take the same fraction, have the same probability of getting the loan. All right, so a bit better one is equalized odds, also called equality of opportunity, which says that the same fraction of qualified people should receive a loan in the majority group as in the minority group. Okay, that seems more reasonable. Okay, the problem is it doesn't take into account historical discrimination, right? Because a person may come out as qualified for a loan as measured by various indicators, okay, due to historical patterns of discrimination as opposed to the inherent financial responsibility of that individual. So you may want to account for that. And if so, equalized odds does not perform that task. The same is true of something called predictive rate parity, which is similar. It's actually the inverse, the reverse of that. Okay. Again, we don't account for historical discrimination. So at some point, we have to decide philosophically whether we want to take into account a historical pattern of discrimination when evaluating people for loans. Okay. Once you do that, then you make the ethnic group an explicit criterion in the decision. Okay, because you have to, compensate for the history. That's controversial. So this decision that we must make is highly controversial, but you can't evaluate these metrics until you make that decision. Okay. Now, one way of getting around this is so-called counterfactual fairness, in which you try to isolate the degree to which financial irresponsibility is responsible for past loan defaults, even though you can't observe that directly. And what's done in this field is to build a so-called Bayesian network or causal network that captures the known conditional probabilities and then infers using Bayesian inference the unknown conditional probabilities. Okay, in principle, this may work. The problem is you need enormous amount of very good data to carry out this kind of inference. So it's difficult to implement in practice. Also, I'm not showing you an optimization model for this because we don't have one. That's a research issue. We don't know how to formulate this as an optimization problem. Whereas the other metrics we can write as an optimization problem. In fact, all but one of them are linear. Okay, so that's basically what I have to say. There are some weaknesses in these metrics. I've already mentioned a couple of them. Another weakness I should mention is, who do you consider to be a disadvantaged group to begin with? How do you pick these groups? It's usually done by legal restrictions. Is that adequate? Okay, so that's a fundamentally difficult question that we really don't know how to answer. Okay, so that's it. We have a question here. Let me just have a look, see what it says. What are your thoughts on problem complexity when individuals adapt to the resource allocation being assigned fairly? Yeah. Example you mentioned in the problem of traffic lights, what if travelers learn that choosing a minor street may get them better green than a fair solution? Yeah, so what is the gaming that goes on here? Will people game the solution? Yeah, of course. So that's a game theoretic question. So some people try to address this with envy-free solutions. That is to say, you find an allocation such that no one has an incentive to swap with anyone else, with anyone else's position. Sometimes you can find solutions of that kind. Okay. The problem with those, in my view, is that an envy-free solution may actually be unjust, even though it's envy-free. The two concepts are not the same. So can you find a just solution that's also envy-free? Probably not. Okay. So what do we do in a case like this? Well, you do what you do in ethics generally. So I discussed this in my ethics courses. We have to have consensus on what's ethical. Okay, so we can agree on whether we should game the system. The systems work, more efficiently if we agree we're not going to try to subvert them by gaming. Now, of course, we have the field of mechanism design that tries to prevent that by designing incentives in various ways. So gaming doesn't work. You can use that. But if you look at the way society works, in my view, we hang together primarily because we have consensus on what you ought to do. We have consensus you shouldn't run a red light. We have a consensus you shouldn't murder anyone, you shouldn't break into someone's house or whatever. Okay? All of these can be gamed, but we have consensus on the rules, even though they're not envy-free. So reaching consensus on ethics is an important element in my view. And we need a rational foundation for ethics. This is what I teach in my courses. Okay, so yeah, it's a big question you've asked, but this is the way I might try to respond to it. So I wonder if we have any other thoughts or reactions we should cover.
We have a few minutes. If there are any questions for Professor Hooker, please feel free to post them.
I'll go back to this reference. I should mention with the machine learning attempts at fairness, we have another problem, and that is when we compare two groups with respect to fairness, we're only taking into account the number of people who receive the benefit. That is to say, number who receive mortgage loans or college admission or a job. And we use that as the means for comparison. Whereas the other criteria that I mentioned compare levels of utility. So it's a more complete measure of fairness. It takes into account the actual consequences for individuals of being selected for this or that. Okay, so that's another limitation of simply looking at equity measures, equity metrics, or equality metrics. Doesn't take into account the utility, as opposed to whether a person is simply selected for this or that. Can we ever really create a fair society? Yeah. Well, people have looked at this for a long time. So one famous person who looked at this issue was Immanuel Kant, okay, who was a philosopher, very famous, and he had some very profound thoughts about ethics. And he argued, basically, that when we decide on the rules for society, we should decide on rules on which we can all agree. And this is what ethics does. It's to reach consensus. Ethics provides a framework, a style of reasoning that attempts to allow us to reach consensus on what the rules are going to be if we all play by the same rules. Now, he went on to say that if we can construct an idea like this, he called it the kingdom of ends. If we can construct a society like this, in principle, we don't need any coercion. We don't need to put people in jail. If people will just follow our social contract, okay, just follow what we can agree upon to begin with, then we're going to obey the law, because the law is designed to be something we can all live with. And as a matter of fact, most of our laws are laws that we agree on, and this is why they work. Okay, so we have laws that say you shouldn't run a red light. Okay, this law is not enforced. Nobody enforces it. Rarely is anyone arrested, or receive a fine for running a red light. They have to catch you. Now you can say, well, let's put a camera at every intersection in the city. Well, what are you going to do? You're going to have 500,000 images from New York City every day. Are you going to send out citations to 500,000 people? No. If everyone decides to break that law, there's nothing you can do about it. So the only reason we obey that law and many others is that we agree. So already we have reached this ideal to a great extent, and it's a good thing. Otherwise, we'd live in anarchy. Okay. So yeah, maybe we can't reach perfectly fair society, but I think we can agree to a great degree. In fact, we already have on what we ought to do if we all play by the same rules. Of course, there are exceptions. When it comes to tax law, when it comes to the speed limit, we're all breaking the rules, because we don't agree on those. We have to reach agreement. This is why a polarized society is so problematic. We have to reach consensus, or, in my view, we're in trouble. Okay, so we have some more issues here. Are there models that describe system behavior when unfairness or inequity is enforced? Okay, so I think that the models I'm talking about all have that characteristic, right? So the models are finding an optimal solution that forces an equitable solution. And the solution we get describes what happens when you insist on a maximally equitable or a maximal social welfare solution. Now, this model may not be realistic. It may not what happens in practice, but this is true of all models. In OR, for example, all OR models are simplifications of reality. But I think, yeah, this is what we're already trying to build into models. We want to try to correctly represent what happens when you strive for equity, or strive for cost minimization, or strive for anything else. And then we update and refine those models when we find out when they're not adequate. In the first part, there seems to be a trend to formulate fairness models as linear problems, yeah. Since global optimization of non-convex problems has made a lot of progress, why not expand models to being nonlinear and non-convex? Okay, I'm certainly not opposed to it if we can do it. Actually, there were a few nonlinear models from the beginning. Of course, I think even today, global optimization is a much harder problem than, say, mixed integer programming or convex optimization, right? It's still a much harder problem and difficult to scale up. But to the extent we can, that's great because you have much more modeling flexibility. For example, you can represent non-concave utility functions, things of that kind. If a company has been operating with a current cost minimization model, but then decides to implement equity, the new optimal solution may be very far from the current one. Does this issue arise often? Okay. Yeah, it can be very, very far. But I should say that even though the solution may be very far, the resulting level of utility generally is not very far. And I'll show you an example of that, going back here. So in the health example I showed you, where is it? I'm sorry, let me find it. Here, okay? So if you look on the bottom here, this is the average utility per person in quality adjusted life years if we have pure utilitarian. This is the conventional solution, okay? This is if we have pure equity, pure Lexamax. And you see, there's not a great difference between them. In fact, the solution we choose is going to be somewhere in the middle, maybe even over here, because that's where most of the action is. And the sacrifice at average utility is actually rather small. This is typical. The sacrifice in average utility is not very sensitive to the degree of equity in most cases. And of course, there are cases where it actually increases with equity because we have a more just society, which is more efficient in many ways. Yeah, but the solution itself could be very different, even though the average benefit is not much different. Yeah. Now, is it overcome? Or maybe we don't want to overcome it. Give you an example. One of our colleagues at CMU did a study of building power grids in West Africa. Okay, and solve the problem to maximize utility and to maximize equity. So the problem is to decide where do you build the power lines in the country so as to stay within your resource budget. If you maximize utility, only the urban dwellers get electricity. If you maximize equity, then you have 2 or 3 power lines going out into the hinterland, and most of the city is without power. Okay, both solutions are completely unsatisfactory. All right, so here's a case where you want to change the solution from a purely utilitarian or benefit maximizing outcome. You want a very different solution than that. So I think this is when we want to use equity models. We're just not satisfied with the maximum utility solution. How is healthcare equity in hospitals currently addressed? Okay. Do you see some of the results being applied in practice? All right. Yeah. There's nothing more complicated in the world than healthcare. So it's very hard to say, what's going on. Now, I know more about the national health system in the UK. The official policy in the UK is to maximize qualities per pound, right? It's to maximize benefit per investment. So they calculate, how many qualities do you get for each pound invested? And if you exceed a certain threshold, then you get funded. That's the official. And that threshold is decided upon by some kind of political consensus. As it turns out, that threshold for Medicare, to the extent they use this approach, is about the same, adjusting for the price differences in healthcare. Of course, it's much cheaper in the UK to get healthcare. All right. So that's a purely utilitarian criterion, but it's not the one that's used in practice. Okay, it's just not acceptable. So the one that the equity criteria used in practice are basically ad hoc, informal. There's no systematic approach that's being implemented politically. And that's why we need it, okay? And this is why what I've been describing here is generally not used in healthcare. It's very political. It's very hard to inject a rational solution for equity into a political context because our political systems are largely not functioning very well. Yeah, so I think that's what I have to say. So traditional triage decisions in hospitals, okay, sort of officially are utility maximization. You treat people who can benefit from treated and people who need to be treated. That's a utility maximization criterion for triage. And there are various colored categories, that people have adopted around the world for this. But in practice, okay, there's other judgments that come into play that are sort of informal and ad hoc and on the scene to inject some greater degree of equity and fairness, according to what impresses people, the experts, the doctors, as to what's fair here. Yeah, and it's not done systematically.
This has been a fantastic talk, Professor Hooker, and so much to mull on and so much to think about. I wonder we might need to have you on again at some point for a follow-up chat. But in the interest of time, I was wondering if we could have Chris maybe round us off.
Sounds great. Yeah, thanks. Thank you as well, Dr. Hooker. Really appreciate your talk. So I want to thank everybody for being here. As we just wrap up, we'll say a few things. First of all, I want to invite you to join our community. If you're interested, this sort of thing is interesting to you, and you want to learn more about analytics, you want to think more, you want to network more, well, this is a good place for you. And so we're really glad to have you. Also, if you're already part of the community and you want to be more involved, I want to go ahead and invite you to consider that as well. We are a newer community. We're establishing various things, but there will be ways to help, and the more help we have, the better we are. One of the things, for example, we're thinking about right now is website development. So that may be something you're good at, you're interested in, you're able to help with. If that's you, that would be great. Reach out. You notice Yash's email address is down there as well. You could always reach out to him at this point for more information. I want to ask Annie to just give us a little bit of a glimpse into an event that we're planning into the future. So Annie, you want to just talk about that for a moment?
Thanks, Chris. We're also working with the Philadelphia chapter to do a joint event. Most likely, it looks like we'll be targeting kind of early fall for that event. And the topic is going to be women in analytics. And we really like to look at career trajectory, understand the skills required in the analytics community from an education, from an experience standpoint, understand mentorship, understand just the challenges for women in analytics. And so we're going to cover that in a panel discussion. We're going to have a handful of professionals, both on the industry side and on the academic side. So to those of you on the phone, if you have any women in analytics that you would like to refer to us, I'd point you to Yash's email again. If you have any suggestions, we've been kind of collecting them amongst ourselves and with the Philadelphia chapter. So please let us know if you personally have any interest or have any interesting suggestions for a panelist. We appreciate it.
All right, thank you, Annie. So one more slide. We're going to, actually there'll be one more after that, just saying thank you, but I want to promote for a moment. There are INFORMS chapters all over the place. We happen to be the Pittsburgh chapter, but there are student chapters as well. And Anthony is, I believe, vice president of the Carnegie Mellon chapter. And Anthony started doing a podcast somewhat recently, and I was introduced to it because he asked me to be a person that would interview with him. And so I was able to do that, go down to the CMU campus, and Anthony and I had a really good time just talking about different things that we're doing at FedEx Ground. But I wanted to just bring that to your attention. It's on Spotify. And actually, I believe Anthony's on the call. So Anthony, if you want to say a word about your podcast, that'd be great.
Hey, sure. Thanks, Chris. Yeah, so I'm really excited to start this podcast. We have 3 episodes that are live on Spotify right now. And basically, we'll just be interviewing professors of operations research or operations management, or anything related to optimization, and people who are working in the field, like Chris at FedEx. So it's targeted towards PhD students who maybe need some advice on things to do, or people who are already in the field and just want to hear what others are up to. Thanks.
Very good. Hey, thank you, Anthony. So just wanted to say thank you again for attending today. Really appreciate it. And we look forward to future events and interactions.
Thanks, everyone. Have a good night.
All right. Hey, thank you. Thanks again, Dr. Hooker.
So much.
My pleasure. Yes.
Thank you, guys.
Appreciate it. Thanks, Beth. Thanks, Chelsea. Yep. Appreciate getting us set up here.
Yep, of course. I'm going to end it now if you guys are ready.
All right.
Okay. Sounds good.
Thanks.
Thank you.
Good night.
No problem. Good night.